So we're going to use this method to derive the derivative of the inverse trig functions. The way we derive it, you need to remember properties of inverse functions before we go through this. So remember that the domain of a function is the range of its inverse and vice versa, because what the inverse functions do basically is flip the x and y coordinates. So if we have a function y equals f of x, remember the inverse is denoted f inverse of x. And if you think back to how you find the inverse of a function, like you solve for x, and then there's a step where you interchange the variable names. And that step where you interchange the variable names is really just done so I think the main reason that they have you do that is so you can get another function of x, and you can graph the original function and the inverse function on the same axes and see how one is a reflection of the other, if you remember that, across the line y equals x. But that step where you switch the variables is really just kind of magic that they have you do to graph. It's not really necessary, and I think in some cases it's confusing because people lose the fact that x and y are switched, and that x is really a function of y for the inverse. So anyway, what we're going to do when we look at the inverse function, when we derive the arc sine or inverse sine function, is we're not going to interchange those variables, and you'll see what I'm talking about the next slide. And another thing to remember is that a function has to be one-to-one to have an inverse. And if it's not one-to-one, you can restrict its domain so that it is one-to-one on that domain, and then you can find the inverse. Look at the inverse or arcsine function. So we're going to derive that by using implicit differentiation. And remember, the sine function is clearly not one-to-one because it's periodic. So by convention, we restrict its domain to the interval minus pi over 2 to pi over 2. So here's what we're going to do. We're going to use implicit differentiation on this equation. So here's our inverse sine equation, right? So what does that mean? That means that if I say y equals the inverse of sine x, that means that x equals the sine of y. That's the whole point of inverse functions. So y is inside that sine, right? So what I want to do is find the derivative of this function with respect to x, but using this other function. So I'm going to use implicit differentiation and differentiate term by term. So I'm going to differentiate with respect to x. So the derivative of x is 1. And then using implicit differentiation on this, the derivative of the outside function's cosine y. The derivative of the inside function's y prime. And so now I'm going to solve for y prime. It's 1 over cosine y. So that's nice. I have the derivative of y, but it's in terms of y. It's not in terms of x. I want dy dx. I want a function that represents this derivative. I want a function in terms of x only. So we need to use a trig identity to turn that cosine y into an expression in terms of x. So remember the Pythagorean identity. If I use that, I can express cosine y as the square root of 1 minus sine squared y. And remember, we started out with x equals sine y. So I can replace this sine squared y in this square root with x. So now I can just replace this cosine y factor in my denominator with the square root of 1 minus x squared, and now my derivative is in terms of x. So you go through a couple of things there that are a little bit tricky at first, but if you have a good understanding of the inverse function as a pre-calculus concept, it's helpful to walk through that.